Hi dear students. After the break, before the break, talk about fatigue phenomena and also natural frequency resonance. If the load acting or to apply onto a body is a dynamic load, then we must consider two phenomena: fatigue and resonance. Okay. Now, this video record first study on fatigue failure. I'm going to create the model of an object and say that it is under the action of dynamic load. If it is the case, then the valuable question is that, okay, then while we are using the component under the action of such a dynamic load, that component can be used how many days, how many weeks, how many months, how many years. There will be weather fatigue failure. If the stress at any point, set by the load is less than the endurance limit or maximum equal to endurance limit, then there will be no fatigue failure. Okay, then in the CAT analysis, fatigue analysis in CAT environment, first find the stress distribution, assuming the load as if it were static. If you see that stress, set by the load, when the load reached to its maximum order, maximum value, find the stress distribution. If the stress is less than maximum equal to endurance limit for the material of the object, then that is okay. Fatigue will not occur. But if the stress is greater than endurance limit, then yes. Then need to determine the technical life for the object, determine the maximum number of cycles for the load, and then say that if the object is attempted to furtherly used, although the total number of cycles of the load reach to the limit, if the customer or user tend to continue to use the object, then it is quite risky. The object will be most probably unexpectedly broken because fatigue will occur. Okay, I'm going to create the model of the object. I selected a simple geometry, but the basic things, or the things to do for fatigue analysis are the same. Not a matter object is in which shape. Okay. Open Inventor, and then first create the model of the object. It is a single component. Yes. To be able to quickly complete the model creation stage, that's why I selected a simple geometry. But the things repeat again for fatigue analysis are the same. Not a matter the object is a simple one to its shape or a complex one. Okay, selected one of the coordinate planes, and then it is a right prismatic object. I know it is shape. Dimensional constraint, the size of the sketch in this direction 100. The unit of measurement is millimeter. At the beginning I selected metric unit system. and the height of this part of the figure is 40. Okay, well, for this sub rectangle, let's say the width is 12, height, let's say 8. Okay, unify the regions, have only one region, trimming this boundary, finish the sketching stage, and then apply the process extrusion. Okay, say that thickness of the prism is 10 millimeters. And then here say that object has a hole. Okay, well, hole is to use for fitting this body to the frame of the structure. Okay, started the hole creation process. The diameter of the hole is, let's say, 16, and it is truly extending. Okay, well, relative to this boundary of the surface, it is axis 20 millimeters away. Relative to this boundary, it is, let's say, 20 millimeters away. It is a truly extending hole. It's a simple hole. Okay. Well, objects in this example, say, made of aluminum alloy. Input the material, clicked on this button, and the material is aluminum 6061. Right click and sign. Now, well, after fixing the material, then have a look at, what is the ultimate limit for aluminum? What is the yield limit? Clicked on this button on which we have pencil point. It is to bring this dialog box, and then select physical option, and then in the window can find thermal properties, well, mechanical properties, and strength properties. Well, the yield limit for aluminum, that aluminum alloy is 275 megapascal. Okay, tensile limit 310 megapascal. Okay, from my lecture notes, well, for aluminum alloys, the endurance limit 30% of tensile strength. Then, okay, well, calculate 310 times 0.3. Well, endurance limit can be taken as approximately 90 megapascal. For being a little bit safety side, we use safety factor. For instance, in the analysis, safety factor is 2 or 2.5 or 3. Okay, say that it is 3 divided by 3. So endurance limit can be taken as 30 megapascal. Okay, keep in mind 30 megapascal is the endurance limit. Okay. Save the file in the memory. Save as. Okay. Well, I asked the students to write their surnames and ID number, and then say that it is for fatigue analysis. Let me use this word, fatigue. Okay, and then yes, save the file. Well, it is also recommended and the name of the file, writing the date of studying. For instance, say that it is 1 day of April. Let's say April 6. Okay, and then yes, after the model creation stage, then deal with the fatigue analysis. Select environment step, and then at this point say that be aware, dear students, the classical stress analysis tool of Inventor cannot be used for fatigue analysis. Well, NASTRAN is the software only. Well, we can use NASTRAN, Inventor NASTRAN. By the way, in Fusion, cannot find tool, although Fusion is a very powerful software for engineering calculations, but unfortunately in Fusion at present cannot find fatigue analysis tool. Only in Inventor NASTRAN can perform the analysis, fatigue analysis. Okay, so select NASTRAN. Okay, NASTRAN automatically selects, linear static option as the type of the loading analysis. Well, first, yes, although we know that the load is a dynamic load, but considering it is maximum value and assuming as the loading were as if static, find the stress distribution. If we see that stress distribution is at any point the stress of the material within the material will be less than 30 megapascal. It is the safe endurance limit for that material. Then can say that okay, no need to perform the fatigue analysis because the technical life of the component is unlimited. Fatigue will not occur. Okay, then pass through such a stage. First, bring the cursor to browser, and then if idealization stage has already been passed, clicked on this, and then teach the software that object is not a shell but solid element or vice versa depending on the case. And also in the dialog box, check whether the material of the object is indicated. This means the material has already been assigned. Say OK. And then, bring the cursor to the browser and, expanding the list, dropping the list, clicking on the cross next to this word, it says idealization, and find this icon, and then when you clicked on it is associated cross, you can find the material icon, right click and edit. It is a must to bring this dialog box in performing fatigue analysis, but here skip that stage because my purpose right now is to find the maximum stress assuming the load as if it were static. Okay. Yes, material in NASTRAN knows that material is aluminum 6061, and I talked to the software that object is not a shell, it's a solid body. Okay, and then yes, the boundary conditions. Clicked on constraining button, and here in this example, that is the condition. This object has been tightly connected to the rest of the assembly. This part rigidly. Okay. The surface of the hole has been rigidly connected to the other component. So it's a fixed connection. Okay. At this end, we have a load. Okay. Distributed load. In the example, assume that this is just the finger of the intake exhaust valve mechanism, and well, this end of this finger is loaded by the tip of, let's say, exhaust valve or intake valve while the engine is being used, is run. Yes, this loading is a dynamic load, but as I said, at that stage, my purpose is that whether within the body, when the load reaches the maximum value, there will be stress value greater than endurance limit. Okay, well, indicate the surface. I said that that is the surface. And then, well, the component from this coordinate frame, I see in the y direction, yes, the load is in the y direction, and it is a pushing force applied onto the surface. And in this example, say that it is 5,000, or say that 1,000 newtons. Maximum value is 1,000 newtons. Have few representative arrows to see that it is not a concentrated force but a distributed load, sweeping the density bar to the right, not too much, few millimeters only. Have more than one arrow. It is to notify the users that the load is not a point load but a distributed load. Okay. Yes. And then, well, in this analysis, I'm going to use the default mesh. Okay, generate the mesh, and then the rest. Run the software. Yes, maximum stress. Well, in the vicinity of the surface of the hole, you see it is greater than endurance limit, 39 megapascal. Well, it is greater than endurance limit. This means while this object is being used, one day fatigue will occur. How much the technical life of this object? Okay. Then yes, keep this analysis in the memory. Click on New Analysis button. But here it is important, in the dialog box, setting dialog box, don't forget to select fatigue option, not linear static loading, but multi-axial loading, multi-axial fatigue. Okay. Well, the units, I'm going to use cat model unit. If this cat model unit is the selected one, can see the stress values in megapascal. I know this. Okay. Yes. And then click on OK button. Well, the previous analysis at the browser to its corresponding icon is inactive. Well, the active one is the new analysis. Okay, idealization, clicked on this button and then teach the software that it is not shell but solid element. Material, well, Inventor NASTRAN knows that material is aluminum 6061 and say okay. And then, well, after passing through idealization stage, then find this icon at the browser, clicked on the cross, and then find material icon. Yes, right click the mouse while the cursor is on material icon and select edit option. Okay. Now, in this dialog, don't forget to click on fatigue button and then where teach the software sigma and curve. The characteristic of sigma and curve for this material aluminum. Well, beta is the slope of this part of the curve. Okay. Well, from the experiments, we know that it is 0.25. Okay. This part of the sigma anchor extends from, well, ultimate stress, tensile stress to endurance limit. Okay. Well, this box to write the ultimate limit, it is 310 megapascal. By the way, when I bring the cursor to the box, Inventor reminding me that the unit is megapascal. So, well, 310 megapascal. Well, if the stress is close to ultimate limit, then, well, this point, for this point, the corresponding number of cycles may be in the order of 1,000. We know from the lab experiments it is 1,000. Okay, cycle. Kf factor, this factor is not available. Well, it is not easy to determine Kf factor. It considers Kf factor considering the roughness of the surface and also corrosion, order of corrosion over the surface. Well, a factor is generated. If the factor is not available, then leave the compartment as empty. Well, this box is to write the slope of the sigma anchor after the endurance limit. Well, actually, theoretically, after endurance limit, the slope of this part of the curve is 0. It is a horizontal line. But in practice, well, depending on the number of cycles furtherly while we are using the object in time, well, if the slope were 0, then the life would be unlimited. But in practice, yes, well, the slope may be 0. Let's say 0.5 or even less than this order. Sigma E is the endurance limit. Well, the endurance limit for our case, considering the factor of safety, set at 13 megapascal. Okay, that is the sigma n curve. Say okay. And then close this dialog box. Fatigue button is on. Okay. Well, one more time bring. Probably I forgot to do something. Edit. Okay, that's okay. And then the boundary conditions. Well, this surface is fixedly connected, fixed to the rest of the assembly. And at this end, we have a dynamic load, clicked on load, and then it is a force, but dynamic force. Yes, force. Indicate the surface. Well, force has y component. It is in the positive direction. Here into this box, right, it is maximum value. It is 1,000 newtons maximum. Make it distinguishable by having not one vector, few vectors. So I slided the density sleeve to the right. Okay, then that is the maximum value of the dynamic load. But the load in the example, since the tip of the valve pushes this end of the object, well, thanks to the existence of a restoring spring in the mechanism, the valve, stem of the valve cannot apply tension force, always can apply pushing force, compression force. But the force will change from 0 newtons to maximum 1,000 newtons, and then gradually decrease from 1,000 newtons to 0 newtons. To be able to teach the software that load is a dynamic load, clicked on this button, and then in this dialog box, well, teach to the software that it is a dynamic load. Well, we have two options: dimensionless user-defined, load scale factor versus time. Well, I selected dimensionless user-defined, and then bring the cursor to this row, double click, and then say X column is to write the instant at the beginning of the cycle. Time is 0. Okay, clicked on tab, and along the Y column, write the factor. That factor is to use well, to find the magnitude of the dynamic load at the instant of time. But at the beginning of the cycle, the coefficient force is 0, magnitude of the force is 0, so the multiplicand factor is 0. Clicked on tab key, and well, when the cycle is half, the time is the half of the cycle, half of the period, well, say that half of the cycle 0.5, that time, but actually it is the mid, it is to say not the second, it is to say mid of the cycle, half of the cycle. At the half of cycle, well, the force reached to its maximum order, so the multiplicand, it is the coefficient to use to multiply with the maximum value of the magnitude of the load is 1. Okay, and then at the end of the cycle, well, the duration will be 1. This means end of the cycle. At the end of the cycle, the force will turn back to 0 again. The force, the load will be 0. So coefficient to use, saying coefficient times the maximum value of the load. If the result is 0, then the coefficient is 0. Okay. And then see the load curve. clicked on show plot button. Here's the load curve. At the beginning of the cycle, this period corresponds to the period of the cycle. At the beginning of the cycle, force is 0, and at the mid of the cycle, force reached to maximum. That is the coefficient 1. 1 times 1000 will be the maximum magnitude of the maximum value of the magnitude of the load. And then where the second half of the cycle, force gradually decreases and reach to 0 again. That is the load curve. Okay, clicked on OK button. And then yes, close this dialog box. One more thing, the fatigue setup. At the browser, find this icon, left click, right click, and edit. Okay, we define the changing of the load in a cycle per cycle, but didn't say anything yet about the duration of the cycle. Well, duration of the cycle, let's say, write the duration. One cycle takes 1 second, let's say. Duration, event duration used to determine life. Okay, let's say 1. And then say OK. And then yes, generate mesh. And then solve the problem, run. This running is to determine the technical life duration, how many cycles can have before fatigue failure. Okay, now that is the result, solid life fatigue analysis, and NASTRAN says that in the vicinity of the hole, the stress maximum. For that part, can say for considering the stress at the place where the stress is maximum, can determine the technical life. In the vicinity of this part, the cracks will appear and propagate just when the number of cycles while the object is being used reach to 8.95 10 to the power 10. Okay, if although we use the component such that it dynamically loaded such times, okay, if we still continue to use the object furtherly, then fatigue failure will occur. Okay, that is the total number of cycles to have while the object is being used. Okay, if the loading is repeatedly applied onto the body, total number of cycle of the loading is equal to that much, then yes, that is the technical life, the limit for it is technical life. If this limit is exceeded, then object will be broken. The cracks will appear in the vicinity of this part where the stress is maximum, and then in time propagate, very quickly propagate and the object will be broken. Okay. This total number of cycle can be converted to a normal time period. If you know the number of cycles per day for the loading, then okay, dividing this total number of cycle to the daily cycle can find the result. It is the number of days along such a period the object can be used without fatigue failure, without having fatigue failure. Okay, I think this part is clear enough. And the following analysis, okay, well, for this object, determine the resonance frequencies. Okay, first finish this analysis and then save the file to record, well, all the things, the results of the calculations, the results of the analysis in the memory of the computer. Don't forget, after performing the analysis, don't forget to save the file again. Before the before the analysis, save the file after creating the model of the object, save, and then at the end of the analysis, save it one more time. Okay. Now, module analysis. Clicked on environment step, and then for module analysis, well, can use the classical tool of Inventor. Clicked on this, and then clicked on create study button, and then in this dialog box, select module analysis option. Well, if we know the frequency of the load, well, for instance, well, the dynamic load will be exerted by a mechanism, and the dynamic load is originated from rotating body. What is that? For instance, it may be an internal combustion engine. It is frequency range from 0 to, let's say, if it is the engine of an aircraft, well, for an aircraft engine, the number of RPM may be in the order of 30,000. 30,000 divided by 60, 500 hertz. Well, 30,000 RPM, revolution per minute, divided by 60 revolution per second. Okay, it is hertz. Okay, it's hertz. If we know the frequency range, then select frequency range, and from 0 to, for instance, 500, check whether there will be resonance. Well, in this range, software can output the resonance frequencies. If you do not know the range, then, well, select number of modes, and, well, for instance, default value is 8 resonance frequencies. For this object, let us determine 10 resonance frequencies. Knowing the resonance frequencies, then can select the frequency of the load. If it is caused by a rotating motor, for instance, then select the speed of the RPM of the motor such that it shouldn't be equal to any of the resonance frequencies. Okay, clicked on OK button after this configuration stage, and then the rest. Okay, well, which part has been connected to the rest of the mechanism or assembly? Clicked on this and say that in the example, that surface object has been rigidly connected. Okay, And for finding the resonance frequencies, in the equation we have stiffness and equivalent mass. Well, stiffness is fixed well via selecting material. For aluminum alloy, well, there is a corresponding elasticity. To be able to say that the mass is also an effective term, just indicate where is the earth. Gravity, clicked on this, and then well indicate one of the surfaces. It is perpendicularly oriented with respect to the line of action of the gravity vector. If it is senses opposite, then clicked on this button. But here it is okay. The Earth is under this object at that side. Okay, and the gravity forces are parallel to each other in the vicinity of this object, but they meet to each other at the center of the Earth. Okay. And then generate mesh, and then the rest. Run the software. Yes, I said that 10 resonance frequencies. Well, the first resonance frequency is 1686 Hertz. Well, if the frequency of the dynamic load becomes equal to that frequency, then the object will make such fluctuations. Okay, the object will vibrate with such deflections, oscillations. Okay, maximum displacement. If the frequency is in this order, right click activate, then you see the object will be deformed differently while it is oscillating. Well, if the frequency is equal to that much, right click and then you see a different oscillation in different directions. If the frequency is equal to that much, then well, you see the object will behave like this. Okay, in selecting the speed of the frequency of the dynamic load, if it is set by a motor, then the speed of the motor such that it is frequency should not be equal to those ones. Okay, greater than this or less than this, greater than this, less than that frequency, greater than this, less than this frequency, but not equal to resonance frequencies. If the frequency of the load becomes equal to one of them resonance frequencies, then this object will start to resonate. Okay, while it is resonating, it will take quite strange shapes while it is oscillating, and probably the atomic bonding forces won't be sufficient to keep the rigidity of the body while it is tending to move in such a direction. Atomic bonding forces reach to their maximum values, and then object will be broken. Cracks will appear and propagate, and the object will be broken. Okay, dear students, this is clear, I think. Well, a similar analysis can be performed in fusion. In fusion, okay, quickly I may demonstrate. Well, I'm going to say upload the solid model to fusion, or just create the model using the tools of fusion and then perform the module analysis. save the file one more time to have the corresponding log files in the memory of the computer. It is always a good practice to define the work as a project and having all the files created by the users and also created by the software, log files, data files, etc. within the same folder, within the same address. Okay, now I'm going to open Fusion. So since the software is not Inventor but gonna be Fusion, why not close Inventor and open Fusion. Well, Fusion is compatible with Inventor, can import an Inventor file to Fusion, similarly export a Fusion file to open it thereafter in Inventor. But since the geometry is a simple one, instead of dealing with file importing to Fusion, I'm going to quickly create it using the facilities of Fusion. Yes, Fusion is almost ready, available for my studying. I selected this special folder for this course. I have already created it. And then yes, start from sketching stage. I selected this coordinate plane, this or that, which one, this coordinate plane. Click, and I know the shape of the object. It is width 100. Clicked on tab key, its height is 40. Press enter. And then, there is one more rectangle over there. Clicked on rectangle creation button. And then from here to there, the width is, let's say 12. Okay, height of this sub region is 8. Enter. And then similarly trim this boundary and unify the regions. Finish the sketching stage and then apply the extrusion process. Okay, the length thickness of the prism is 10. And then say okay, new body. In the dialog box, new component. It is recommended. Define the component, define the object as a new component. Okay. Here is the model, and create the hole quickly. Where is the hole? Well, in the dialog box, first select whether it is a standard hole. If yes, then select clearance option. If not, then simple. This one is okay. Not distance, but it is truly extending hole. Okay. Well, it starts from this surface. Its diameter is in the example 16 millimeters, and from this boundary the axis is 20 millimeters away. From this boundary the axis of the drill is 20 millimeters away, and then say OK. Yes. Input the material. Yes, of course. How? Modify. Click on this listing button and select physical materials option, and then in the dialog box, here it is, select metal option, and then find the material in the list, aluminum 6061. Hold it with a left click and drag the mouse toward the model, and then release the button of the mouse. That is the thing to do in the procedure for inputting material in Fusion. Okay, save the file. Okay, click on save, and then yes, the folder is the location is the correct folder. Write the name of the file, surname, ID number, and this is for module analysis, for resonance, for determining resonance frequencies. So write resonance, and date of studying April, let's say 6. Okay, and then well, model creation stage is okay. Well, no need to keep this browser after selecting the folder and the file. Then toggle off this button, have the working area greater in size, fit to the screen completely, and then yes, click on this listing arrow and drop the list. In the list, find simulation option. It is first to bring this dialog box. In the dialog box, well, the studying is for determining model frequencies, resonance frequencies. So make the selection on this one with a click, and then click on create study button. Okay, and then the rest constraints, click on this and say that this surface has been fixed connected. Okay, and well, for allowing the software to determine equivalent mass, well, say loads, select toggle gravity on option, and then yes, if the gravity sense of the gravity vector is correct, that is okay. If not, then bring the cursor to the browser, find load icon, and then clicking on the listing arrow, find gravity option, and then bring the cursor onto the pencil point. It is to bring the editing dialog box. If the location of the earth is wrong, arrowhead is toward the earth. If it is in the wrong direction, then click on this and reverse it, flip flop. And also in the box, check whether this gravitational acceleration is correct. Yes, everything is correct. And then the rest. Generate mesh, drop this list and then generate mesh, or bring the cursor onto mesh icon, right click and select generate mesh. If necessary, then well, use finer mesh. Okay, how? Local mesh control, use finer mesh in the vicinity of this hole, let's say. Okay, after making such a changing, then well, we have exclamation mark at the browser. Fusion says that the mesh is to regenerate mesh. Okay, local mesh control, have a look at 3 millimeters, well, furtherly decrease to, for instance, 2 millimeters as the mesh size, and then well, rerun the parts for generating the mesh again. Right click and generate mesh. Yes, you see in the vicinity of the hole, the finite elements are smaller in size. Okay, well, if necessary, well, use finer mesh. And then the rest. My purpose is to find, our purpose to find the resonance frequencies. Then, okay, well, clicked on solve button. Yes, you know, the solution is held on in the host computer of the company. And okay, clicked on solve button and then wait for a while. Depending on the speed of internet connection and also the crowdness of the traffic, well, lots of researchers, engineers, designers, users sending problems to the host computer of company, then need to wait too much. Yes, solve this problem. Data is sent to the host computer, is being sent to the host computer of Fusion, and then over there, depending on the length of the queue, need to wait, well, maybe few seconds, minutes, even hours. Okay, well, pause the record here. Okay, well, the solution has been completed in the host computer, and then see the results, the resonance frequencies. Yes, module analysis been completed. Well, how many frequencies we have? Well, in the default configuration of the software, 8 frequencies are generated. Well, resonance frequencies. If the frequency of the dynamic load is equal to that much, then resonance will occur. While it is resonating, the body will fluctuate like this. If the resonance frequency is this one, you see fluctuations are different. Well, if the resonance frequency is equal to that much, equals to that much. Now, well, to be able to prevent, say, resonance, this means the dynamic load frequency of dynamic load must be different than those resonance frequencies. Well, by the way, to be able to configure the software for outputting not 8 resonance frequencies but more resonance frequencies, well, okay, well, there's a configuration stage at the beginning. Well, configure the software. Clicked on finish result button and configuration stage settings. You see select settings option, and then here number of modes. Default value is 8, or say if you know the frequency range, then select this one and then say well, the resonance frequencies are to be determined from 0 Hz to, for instance, 1000 Hz. Okay, well, which one is the case? Then if you know the range, then you can select this option. If not, then say that have a look at the resonance frequencies, and accordingly thereafter can select the speed of the motor, frequency of the motor, or the frequency of the dynamic load accordingly. Then into this box, make a click, and then write. If you're going to determine 8 frequencies, it is okay. If not, then change the number. Say that 10 frequencies. Okay, dear students, if you want to see the results again, bring the cursor on the result icon and then select view results after right clicking. Yes, here is the result. If the frequency of the loading is 20, yes, am I true? 20.1 kilohertz, then the object will resonate while making such fluctuations, being in such deformations. Okay. And well, if atomic bonding forces cannot balance the stress values, then object will be broken, of course, resonate and broken. Okay, dear students, um, well, completed my lecture and cat demo. That's all. Okay, under the title. Have a nice day. Bye bye.